this video, we will be building a decentralized exchange on Rootstock blockchain. Before we proceed into that, let's first understand what Rootstock is. So Rootstock is a smart contract platform secured by Bitcoin that brings Ethereum-compatible smart contracts to the Bitcoin ecosystem. It allows developers to build decentralized applications using Solidity while benefiting the Bitcoin's security. Key features of Rootstock are like the Bitcoin level security. Rootstock is secured through merged mining with Bitcoin inheriting the Bitcoin hash power. This makes it one of the most secure smart contract networks available. Rootstock is also EVM compatible, that it's fully compatible with their Ethereum virtual machine, that's EVM. So developers can deploy their Ethereum smart contract without rewriting their code. It's also a smart Bitcoin, that's RBTC. So Rootstock uses RBTC, that's 1:1 like with Bitcoin as a native gas token. BTC can be locked on Bitcoin and used as RBTC on Rootstock for transactions. Rootstock also gives a lower transaction fees compared to Ethereum mainnet. Rootstock offers significantly lower gas fees. This makes it quite suitable for a real world and enterprise grade applications. Also, the transaction that happens on Rootstocks are quite faster. Rootstock has faster block time than Bitcoin, enabling it as a quicker transaction. Confirmations, that's ideal for DeFi payments and tokenized assets. So now we'll go on in what all prerequisites are required for building this project. The first is Git. So just click here Git. So Git is a distributed version control system that is used to manage and track code changes. So it allows a developer to collaborate efficiently and maintain its code history. Also, it can roll back to the previous versions when needed. So from this gitscm.com, you can install it in your PCs also. So here is for install for Windows. You can just click here and install this Git. Then next will require Foundry. So get Foundry. So Foundry is a fast and powerful Ethereum development toolkit that includes Forge for building and testing smart contracts and Cast for interacting with deployed contracts. So it supports a Solidity natively and this provides advanced testing, scripting, and debugging features. So we have used Foundry this project to compile the contracts, run tests, deploy. So there are steps to download the Foundry. So you just go to this website, getfoundry.sh, and you just get this command on your terminal and download the Foundry. Then next is Node.js. So Node.js is one of the free open source cross-platform JavaScript runtime environment that lets developers declare servers and web apps, command line tools, and scripts. Here you can just go click here on get node.js and you can just download node.js from here for Windows, or you can even do it for Mac OS, Linux, AX accordingly. Then we'll go for seeing a wallet. So metamask.io. Go to this website because we'll require a wallet. Click on get MetaMask and then it's redirecting me to the MetaMask because I've already installed it. But if you're new to it, you can just install it. Then go to chainlist.org. From here, you can search any network. I'll just include testnet and I'll search for Rootstock testnet. So you can just simply add it to MetaMask here and you can just confirm because we are updating it to Rootstock testnet. You can do it for mainnet as well. Or for any network that you want, you can, through Chainlist, you can add it to your wallet, whichever you have downloaded. Then we'll go for searching Rootstock faucet and then here Rootstock faucet. And we'll just from MetaMask, we'll put a public key. I'm taking in my public key Rootstock testnet here and pasting it. Clicking I'm not the robot, and I'll get the RBTC. So this Rootstock RBTC faucet is to get free RBTCs, test RBTCs, that are the testnet version of RBTCs. It's sent successfully to my address. So these are used for development and testing purposes. It is no real monetary value. It just we can deploy, test, and interact with smart contracts without spending the real fund. So this were the main prerequisites required. Also, we will see Rootstock RPC URL. So for mainnet, we have this URL as https public node rsk.co, and for testnet we have this. So for mainnet we have chain ID 30, for chain ID 31 for testnet. So we can have the RPC URL as well, that are the endpoint for deploying or interacting with the contract. So that's all the prerequisites we are required to know to build this project. Now let's go on building this project. So now let's proceed on understanding decentralized exchange in depth. So decentralized exchanges are peer-to-peer platforms on blockchain networks that enable cryptocurrency trading without intermediaries like centralized exchanges. They use smart contracts to facilitate direct swaps between user wallets, maintaining a non-custodial control of funds. So the key features of DEX are like DEX operate via automated smart contracts on chains like Ethereum or Solana, allowing a permissionless access and trustless transaction. Users retain custody of assets, avoiding risk from hacks on centralized platforms. They support diverse tokens and multiple blockchains. So, like, how does a DEX work? So, trades occurs through liquidity pools where user deposit token pairs like ETH, USDC to earn fees rather than a traditional order book. Algorithms like constant product formulas like x into y will give you a constant, determine prices dynamically based on supply and demand. Users connect wallets like MetaMask, approve transactions, and swap instantly with the gas fees, covering all the network costs. Now let's understand what is the difference between DEX and centralized exchange. So DEX is a decentralized exchange, that is, there's no custodian, whereas centralized exchange is custodial. In DEX, the intermediary is none of the smart contracts, whereas in centralized exchange, the intermediary is the central authority, and the access in centralized exchange is the account registration or the KYC, whereas in DEX, it's wallet based global. Like popular example of DEX is the Uniswap. So now let's understand what are the advantages and risks of DEX. So DEX is offered as enhanced privacy with no KYC requirements and resistance to censorship or hacks targeting exchange funds. However, they face challenges like high fees during congestion, impermanent loss for liquidity providers, and smart contract vulnerabilities, front running by bots, and lower liquidity for niche tokens. Now, let's go and see what actually Uniswap looks like. So, this is their website, app.uniswap.org. So, you can just open that app. It's one of the popular example of DEX. So, here you can just swap anytime, anywhere. You can go here, connect. You can connect your wallet. So, just connect your wallet, come connect. So it will connect Uniswap to the MetaMask wallet. Now here you can swap. So if I click here and go on selecting Tether, so I can just sell Tether, and for buying purpose, if I go on selecting Ethereum, so if I sell about of my Tether, I can buy in 100 Tether, I can buy about 0.033589 of Ethereum, and just here click on add funds to swap, and it will immediately swap it. Now we'll see what AMM is. So AMM is an automated market maker which replaces traditional order books with liquidity pools where user deposit token pairs and an algorithm sets the prices. Examples like Uniswap, PancakeSwap, and Curve, which dominates SpotDex volume by offering simple swap US and yield for LPS. So, like benefits of AMM is that it is a decentralization and permissionless access. Then it has a continuous liquidity of passive income opportunity. But still, there exists some risk like impermanent loss, slippage, contract vulnerability. So this can be seen in AMM. Now let's see what are order books. So order book decks mimic on the centralized exchange behavior by listing bids and asks and matching them via matching engine. They support market and limit orders and attract road traders who want precise control over their execution and order types. So some key features of order book decks is the user control. The traders set their own prices and the quantities, and there is complete transparency. Then there's autonomy, where the user can maintain the custody of their funds. Then, of course, there's an efficiency in this. But some challenges faced to the order book deck is its speed, scalability, the gas fees, and the liquidity. Then we'll see what on-chain and off-chain order books are. So on-chain order books or decks stores all the orders and matching logic directly on the blockchain. That leads to maximizing the transparency but paying gas for the update. Off-chain or hybrid order books keeps the book and matching on servers while setting trades on-chain, improving the speed and throughput at the cost of some decentralization. The advantages is its speed and efficiency, low cost, improved liquidity in off-chain, whereas the advantages seen in on-chain is its transparency and trustlessness, the security and non-custodial, and the censorship resistance. Now let's see the DEX aggregator. So DEX aggregators are like 1inch or Paraswap, routes a single trade across multiple DEX to get the best effective price at lowest slippage. So they analyze the liquidity across many pools and order books and split orders when needed to optimize the execution. Then we can see hybrid DEX. So hybrid DEX just combines AMM pools with an order book front end or a dual engine. So users can either swap their pools or place an advanced order. So many 2025 era platforms use such hybrids plus external aggregators to give centralized exchange like performance while preserving some self custody. So, like key features of using a hybrid DEX is it offers the best of both the models. So, it's non custodial asset management, there is high speed, a good scalability, with an enhanced liquidity, also a improved user experience because it also resembles our traditional centralized exchange, but some advanced trading tools has got into it. Then there's a regulatory compliance and some advantages can be seen throughout. So this was all about decks that we have seen. Now we'll go on building our projects. So let's first do the environment setup. So here in this RSKDex, we'll create a new folder and name it as RSK_Dex underscore swap. And now we'll open a terminal. So here I've opened git bash and first I'll give cd and I'll direct the file. Then the command that will give is forge init. So this forge init is used to set up a new Foundry project and it automatically creates a standard project structure with folders like SRC for smart contract, test for solidity, base test, and scripts for deployment, and lib for external dependencies. Also, there are some important files included like founded, so mill we can see or perfect ignore. Next command is for installing some extra dependencies that we want. So forge install Foundry rs/forge std. So this command is used to add the forge std, which is Foundry's official standard library for testing. So it provides essential tools like the test-based contract, powerful VM cheat codes for manipulating blockchain state. Now next we'll be installing the OpenZeppelin contract. So forge install OpenZeppelin/OpenZeppelin contract, and we'll run this. So this will install the widely trusted OpenZeppelin contracts library, which will contain secure, audited, and usable implementations of common standards such as ERC20, ERC721, access control, and security modules, allowing the developers to build robust smart contracts without reinventing the core functionality. Now let's go on understanding. Till it's getting installed, we'll understand what all files and folders that it has created. So first, let's see script. So script contains deployment and automation scripts. This folder contains the Foundry script used to deploy smart contracts and automate blockchain tasks. So we already have the installed script here, rewritten script. So we have just deleted it because we'll be writing our own script in it. Then let's see what SRC is. So we already have our contract. So SRC is the folder that contains the core Solidity smart contract and define the business logic of the project. This is kind of the heart of the application. All rules, permission, and the state changes live here and are executed on chain. It's the main protocol contracts where it contains. Then we have tests. So tests hold all the automated tests and files written using Foundry. The smart contracts are immutable once deployed, so they must be thoroughly tested before going live. So automated test just helps us catch the bugs early. So it contains a test that simulate real user interaction, edge case, and failure scenario tests can be seen. Then we have git ignore. So git ignore, in this folder of git ignore, we have the like this tells git which files and folders should not be tracked in version control. So it exists just because there are some files that are generated automatically. They're quite environment specific or sensitive or temporary. Then we have Git modules. So Git modules tracks Git submodules used by the project. It exists because Foundry installs dependencies like OpenZeppelin post standard that we just installed as submodules. So it contains the dependency repository URLs, the local paths inside the library function. Then we have foundry.log. So foundry.log is Foundry's dependency log file. It the pins the dependencies for exact commit hashes, ensuring that there is consistent builds. So it just logs open applying contracts and post standard library there. Then we have foundry.toml. So this Foundry configuration file defining compiler version, optimizer settings, RPC endpoints, and project behavior. So Foundry.toml is the main configuration file for Foundry. It defines how your smart contract are compiled, tested, and deployed. Instead passing options every time in the terminal, this file centralizes all the project-wide settings in one single space. Then we have README. So README is a high-level overview of the project. Its purpose, the features, setup instructions, and usage guide. There is a main documentation file of the project. It gives readers a high level understanding of what project does and how to work with it. So now this will go on writing our code. So now let's begin our project. Now we'll go on writing the smart contract first. So in SRC folder, we'll create one file and we'll take. So in this, we'll be writing the main Dex smart contract that will manage the liquidity pools, local swaps using the AMM model. Also, it will handle the liquidity addition, removal, swaps, and fee calculation securely on Rootstock. So let's go on writing it. First, we'll give our license identifier, ID, and now we'll give Solidity compiler versions, that is Solidity, and let's get the version at 0.8.1. Now we'll import. So import, first we'll be importing IRC20, C20, and we'll be importing this from OpenZeppelin contracts token slash ERC20 slash IRC20.so. Next, we'll be importing safe ERC20, safe ERC20. We'll be importing this again from open slash token slash ERC20 slash the safe ERC. So this import will provide us a safe token transfer method to the prevent any errors. Then again import ownable, import ownable, and importing this from OpenZeppelin contract access ownable. So this import will provide an ownership access control to the like owner only function. Now next will be reporting, then transfer card. So this will be importing from. So this will be importing from the open bank contracts only. So this import will protect against whatever transfer attacks are there in the functions like swaps. Then again we'll go on importing maths. So for the calculation that will be occurring, as in this we will be doing a price calculation. As I said, this is the heart of the project. So it will contain everything from price calculation to the liquidity pools, using slash maths slash math dot. So here we are done with all our inputs. Now we'll be going on give it a contract. So contract will give it as RSKDex is ownable in transit card. And inside this, we'll be giving using safe ERC20 or IRC20. IRC20. This will just enable the safe transfer and safe transfer from for ERC20. Next, we'll be using maths for UNT 256. This will enable all the math functions like square root on UNT 256. Now we'll go on giving the event. So event liquidity added, and inside this we'll give address indexed provider. This will give the liquidity provider address. Then we'll give UN2 for token A amount. So this will give the amount of token A that has been added. Similarly, we'll be giving this for token B amount as well. Then we'll be giving for our liquidity. So this will give the liquidity tokens that have been minted. Then another event will give it as liquidity removal. Liquidity removed. In this, similarly, we'll give address. Similarly, we'll be giving all of these others. That is the liquidity provider address, amount of token that has been removed, and the token amount of token B that is removed, and the liquidity that is burned. Here we have added this amount and the minted liquidity. Next, we'll give another event for swapping. So event swap. In this, we'll give address index user. which will have the swapper address. Then we'll give address indexed token in, which will have the token sent to the pool address. Then address index token out, which will be token received from the pool. Then we'll have UN256 and UN256 amount out. That will have the input token amount and here the output token amount. That now we'll use the pool structure. So let's begin with struct pool. In this, we'll be giving IRC20A token A, which is the first IRC20 token. Similarly, we'll be giving for B as well. That will be the second IRC token. Then we'll give UN256 reserve A. So this will be a current reserve for the token A. Similarly, for B, that will be a current reserve for token B. Then we'll give the total supply. That will have the total liquidity tokens in the pool. Then we'll give last. That will be the product of reserves after the last liquidity event. Then we'll do mapping. So mapping from address, we'll be mapping it to UN256. So this will just track the liquidity per user. Now we'll be going to the state variables. So first we'll do mapping again. Mapping from bytes 32 public pool. So this will map the pool ID to pool data. Then we'll again do mapping. So mapping from bytes 32 to bool. And we'll also give this public saying that pool exists. This will track if the pool exists or not. Now we'll give UN256 public constant. So we'll give the denominator numerators. UN256 public constant, and we'll give the denominator that's equal to 1000. We are just giving that fee denominator for 0.3% of the fee. As you can here, 1000. Similarly, we'll be giving it for numerator as well. The numerator. That this will be equal to 3. Now we'll give it for minimum liquidity. So UN256 public constant for minimum liquidity, that is equal to 10. So here the minimum liquidity is locked. This is we have mentioned it. Now we'll go for the price oracle storage. For that, we'll be doing mapping first. Mapping from bytes 32 to UN256. And here we'll give public and the price 0 cumulative last. Price 0 cumulative last. So this will be the cumulative price of the token 0. Similarly, we'll be doing mapping for bytes 32 to UN256. That will be public, and we'll be doing this for the token 1 now. So public price 1 cumulative last. This will be the cumulative price of token 1. Now we'll give the block timestamp. So mapping from bytes 32 to UN256 public and the public and your block timestamp last. That's a last timestamp for the oracle. Now let's go for giving the constructor. So constructor, that's ownable, and so here we are setting the deployer of the contract owner. Now we'll have the pool management. For that we'll be giving function as create pool. Inside this will have the address of token A, address of token B, address of token B, and then we'll be returning it externally. So external returns bytes 32. So this here we have created the function. Inside this we'll be giving require, that is token A is not equal to is not equal to token B. The first condition that we want, the token A and token B should not be equal. And if it is, then it's like identical tokens. So this is to ensure that the tokens are not synced. Again, the next require will statement will be giving us require token A is not equal to address 0. So there must be a valid address for token A and will be given and operator, and token B also should not have a invalid address. So both will be giving the same conditions. So if so, it will give 0 address. So here we are ensuring that there is no 0 address for both token A and token B. Now we'll be sorting the tokens. So address token 0, then address token 1, address token 0, address token 1. This is to be equal to token A less than token B, and we'll be using a conditional operator here. That is token A, comma token B, token B, comma. So here we are sorting tokens to ensure that there's a consistent pool ID regardless of the order which has been followed. So here I will give the pool ID. Pool ID is equal to 256 ABR.0, comma token 1. So it will generate a unique pool ID. Then we'll give require, that is not pool exists, the pool ID, comma pool already, so it will display pool already exists. So this is for that pool must not exist already prior. So for that we have given this. Then pool storage pool, that will be equal to the pool ID. So this is for the reference to the new pool. Then pool dot token A, that would be equal to IRC20 and token 0. We have set token A here. Now similarly, we'll be setting token B. Dot token B, that is equal the pool ID. This will be equal to true. So it will mark pool as existing. And now here we'll be returning the pool ID. Now we'll add the liquidity. So for that, we'll be giving a function as add liquidity. In this, we'll be mentioning bytes 32. Then the amount A that's desired, the desired amount A will be there. We'll give it as amount B desired. Similarly, for the desired amount for B, amount B desired. Then the minimum amount for A, we'll give it as amount A min, amount B min. And we'll give the address external and a non-reentrant. So we give this non-reentrant to prevent the reentrancy attack. So returns U into 56 amount A, U into 56 amount B, and U into 56 liquidity. Now we'll give a require. In this, we'll give require and we'll check the existence of the pool. So we'll show its exists. So pool exists, the pool ID, and we'll give the pool does not exist. Pool does not. From this, we should get the pool should exist, must exist. Then pool storage pool, that would be, so that is pool. So this will get the pool reference. Now we'll go on calculating the optimal token amounts. So that will give amount of A, amount of B, and this would be equal to add liquidity in pool, the amount A that is desired, amount B that's desired, the minimum amount, and the minimum amount of B. So it will just calculate all the token amounts. Now we'll be going on transferring tokens. So this will be a transfer of tokens from user to contract. So pool dot token A dot save the address of this. And similarly, we'll be doing it for token B. Let's just copy paste and see what changes will be requiring. So here instead of token A, we'll be doing token B. and here the amount of B will be done. Now we'll go on minting the liquidity tokens for the users. So for that, we'll be giving liquidity will be equal to underscore mint and pool two, pool common two. So we'll be liquidating tokens for the user. Now we'll be giving an emit liquidity added, and so that will be giving two amount A, amount B, and the liquidity. So this will just emit the event. And now here as we have added the liquidity, similarly we'll be going to remove the liquidity. So now we'll create a function as remove liquidity. In this function, we'll be giving types 32 pool ID going to in amount in. So here we'll be giving amount minimum, and similarly we'll give it for B as well, going to 56 minimum amount of B, and then address 2. Now we'll give this externally external non return returns UN256 amount B, and then we give required pool exists the pool ID, and we'll give this as pool does not exist. Similarly, we'll be giving pool storage. So as we did in pool storage pool, this will be equal to pool ID. So this is just as a pool reference. You can get the pool reference from here. Then we'll go on burning the liquidity tokens and return the token to the user. For that, we'll be giving amount A, amount B, and this would be equal to burn pool liquidity. So this will burn the liquidity token and return the tokens to the users, and require amount A that is greater than equal to minimum amount of A. So this will display insufficient amount. It will just validate all the minimums for A as well as B. Similarly, we'll give this for B as well. So require amount B that has to be greater than equal to minimum amount of B. This will display insufficient. Now we'll give emit liquidity removed, and so this will give 2 amount B and liquidity. This will emit the event. Now we'll go on swapping function. So we'll give here the function as function swap. This will give by 32 the address of token in, then the UN 256 amount in, the amount out, the minimum amount that's out. So for that we'll give amount out min and address to address to. Now we'll give the external non-reentrant returns and the amount out, which is as 1 to 56 amount. Now we'll give required, and inside that we'll give pool exists, the pool ID, and pool does not exist. Similarly, we are doing it. Pool does not exist. Pool storage pool that is equal to the pool ID. So here again we are getting the pool reference for swapping the function. Now we'll be validating the input token. So require token in, and it will check. So that equal to address of pool dot token. Also an operator that will also check that token in has an address of B, address pool dot token B, and this will give us invalid token. Invalid token. Now, after validating this input token, now we'll go for a boolean. So bool is token A equal to token in equal to address of pool dot. So this will determine which token is being taken as an input. Now we'll just get the results done. For that, we'll give uint 256, uint 256 reserve in, reserve that is equal to its token A. We'll give the conditional operator. The pool dot reserve A dot reserve A, the pool dot reserve B, and we'll just swap it. Pool dot reserve. We'll be calculating the output amount out, that is equal to get amount out, and this will give amount in, the reserve in, and reserve out, and we'll be giving require out, which is there, amount out that has to be greater than equal to the minimum amount that's out. So amount out minimum, so it will display insufficient output amount. Insufficient output amount. So here we are calculating the output amount. Now we'll transfer the input tokens to the contract. For that we'll give IRC20 and token in, the message dot sender, the address of this, and the amount in. So here we have transferred this input tokens to the contract. I will update all the reserves and transfer output tokens to the user. So for this, we'll be using our if else loop. If it's token A, and we'll give pool dot A, and we'll just give an increment amount in. So similarly, we'll be doing it for B as well, but here we'll give reserve B in the amount out. And now we'll transfer. So first we have updated this reserves in this two statement, and now we'll go on transferring. So pool dot token B dot save transfer to amount out. So here we are transferring the output tokens to the user. Now we'll go for else. Similarly, we'll be doing it for B to A. So now we'll just change or replace A by B by A. So also the pool dot token instead of B will be doing A. Now we'll go on updating the price oracle. So here underscore update pool and the pool ID. So we are updating the price oracle. Now we will be giving emit swap message dot sender or token in. Then is token A again. We'll be giving a conditional operator is token A. The address of pool dot token B. Then the address of pool token pool. Then we'll give amount in and the amount out. So this is our emit. Now we'll go on proceeding with AMM formulas. Whatever the mathematical operations that will be occurring in the project will be done here. So function get amount out UN250 in, then the reserve in, so for that UN256 reserve in and reserve out. UN256 reserve out. Your returns UN256 amount. In this, amount out has to be greater than 0. If not, it will display insufficient output amount. Then require the reserve in has to be greater than 0. Also, the reserve out has to be greater than 0. So if the both conditions are true, then there will be sufficient liquidity, and if it is false, you will display insufficient liquidity. Then UN 256 will give the numerator, denominator, and whatever the amount in will be. So UN 256 numerator, that is equal to reserve in plus the amount out, or reserve in into the amount out into the P denominator. Similarly, for the denominator, we'll give a UN 256 denominator that would be equal to reserve out minus the amount that is out into the P denominator minus P numerator into P denominator minus numerator. So this will give us the denominator. So the amount in finally would be amount in is equal to numerator by denominator plus 1. Then I will go for giving the pool info. For that, we'll create a function as get reserves, function as get reserves, and in this will give bytes 32, an external view returns, and then in this will give the reserve A and reserve B. So U into 56 reserve A and U into 56 reserve B. In this will be giving the pool info. So pool storage pool is equal to the pool ID. So is equal to pool ID. Done. We'll be returning return pool dot reserve A, comma pool dot this will return the current reserve. Now we'll be creating another function as get user liquidity, and then we'll give bytes 32 pool ID, the address of the user, give us externally, so external view returns, and the UN256. In this, we'll be returning the user's liquidity or return pool ID dot liquidity user. So this has returned the user's liquidity. Now we will create another function as get pool ID. So function get pool ID. And this will give the address of both the tokens A and B, address token A and address token B. And will purely return this externally. So external pure returns and will give bytes 32. Then here we'll give the address of token 0 and the token that is created. So address of token 0, address of token 1, and with the another conditional operator will give the conditions and the statements that has to be executed according to that condition. So token A, if less than token B, then we'll just go on swapping token A and token B. So if that's true, it will give token A and then token B. Otherwise, it will just swap it and give token B, then token A. KCAC 256 BI dot encode fact and token 0, token 1. So here we are deterministic the pool ID. Now we'll go for doing all the internal functions. So for that, we'll be creating a function named as add liquidity storage pool, the desired amount of A, then the desired amount of B, minimum of AB. That's all we'll be requiring. So amount B desired, then the minimum amount of A, minimum amount of B, and then we'll give this all internally as we're writing all the internal functions. So internal view returns, UN256 amount A, the amount of B as well, amount B, and in this we'll be giving our if else statement. So if give the condition here in this is dot reserve A, pool dot reserve A is equal is 0, it will check whether it's 0. Also, it will check for B as well. It will check if the pool is empty and take all the desired amounts. So amount A, comma amount B, that would be equal to the desired amount of A as well as the desired amount of B. Else, will calculate all the optimal ratio in this else. If this statement is false, then you can execute all the, or it will calculate all the optimal ratios. So you in 256 amount the optimal, that is equal to the amount desired into the pool dot, and this divided by the pool dot reserve A. Pool dot reserve A. Now we'll be giving another if loop, that is if amount be optimal, is less than equal to B, and we give the require amount be optimal, that is greater than equal to the minimum amount of. So if this doesn't happen, it will give insufficient the amount, then amount B will be equal to the desired amount of A. Amount A will be desired amount, whereas the amount B will be the optimal amount of A. And for this, if we'll give else UN 256 amount A optimal. So now we'll do it for A. So UN 256 amount A optimal will be equal to the desired amount of B into the pool reserve for A, pool reserve, the pool dot reserve B. Then we'll give assert amount A optimal, that is less than equal to the desired amount of A. Then we'll give require amount A optimal, that's greater than equal to the minimum amount of A. It will give it as insufficient amount. Now amount A, amount B. Amount A will be given by the optimal amount of A, amount A optimal, and B will be given by its desired amount. That's it. That was our else loop. From here we have this else and this else inside it. That's the nested loop here. Now we'll be creating another function for minting. So function underscore mint pool storage pool and address to internal function. So internal returns the UN250 and UN256 balance A, that is equal to the pool token A balance of the address. Balance of address. This. Similarly, we'll be doing the same for B as well. We'll be closing this off. So here we'll be replacing the A by B. So here we are checking balance of both A and B token. Now we'll give UN A, that would be equal to the balance of A and reserve of A. Similarly for B, we're checking about amount of B. So it will be balance of B minus the pool dot reserve B. Now we'll give the if loop to check the total supply. So if loop, and the condition we'll be giving inside it is that pool dot total supply is equal to 0. So this condition is true, and liquidity is equal to your math dot qrt square root of amount A into amount B minus the minimum liquidity pool minus minimum liquidity. Then pool dot total supply would be equal to the minimum liquidity. So here we are locking the minimal liquidity, and then we'll give else the liquidity is equal to math and the amount A into the pool dot total supply, that's divided by the pool dot reserve and the amount into pool of total supply. Similarly for B, amount B into the pool dot total supply into the divided by pool dot reserve. So we did same for both A and B. Now we'll complete the loop here and we'll give require liquidity that's greater than 0. If it's not, it will display insufficient liquidity min. Now we'll assign some liquidity tokens. So pool dot liquidity 2 and we'll assign it liquidity. So here we are assigning the liquidity token, and then we'll be once we have assigned the token liquidity tokens, we'll be updating the total supplies. We have updated the token supply here, and now we'll be updating both the reserves for A as well as B. So this will be equal to balance of B. Now we have completed our mint function. Now we'll be writing our burn function. So function burn. So pool storage pool, and then we give it 1256 liquidity. Then address to internally returns amount A, amount A, and amount A and amount. Now we'll be giving require, that is pool dot liquidity, require pool dot liquidity message dot sender, that would be greater than equal to our liquidity. If not, it will display insufficient liquidity. Then we'll be giving the balance of A. So uint balance A is equal to the pool dot token A. That's the same that we did here. Similarly, we'll be doing it for the balance of B as well. So, and now we'll give the amount. So, amount of A would be equal to the liquidity into balance of A, liquidity into balance A divided by the pool dot total supply. Similarly, the amount of B would be the liquidity into balance of B divided by the total supply. Then we'll give the require statement, require amount of A that has to be greater than 0. Also, amount of B has to be greater than 0. If this doesn't happen, it will display insufficient liquidity bond. Now pool dot liquidity message dot, that would be equal to the liquidity minus liquidity. And similarly, you can see the bond and total supply as well. So here we are sending our tokens to the users A and B. So from B, so here we'll do for safe transfer for B as well. Now we'll update the reserves for both A and B. So pool dot reserve, that would be equal to pool dot token A dot the balance. Similarly, what we wrote up at this. So here we have updated the A reserve. Similarly, we'll do it for B as well. So pool dot reserve B is, that would be equal to pool dot token B dot balance of addresses. So we are done with our bone function as well. Now last function that would be creating is function update. So function update will be doing it. So pool storage bytes 32. The bytes 32 is pool ID. This internal UN 32, that would be equal to UN 32 block timestamp. So the mod will give 42, this is 32. So here we're giving the current timestamp to it. UN 32 time elapsed equal to the block timestamp minus the block timestamp last, the pool ID. Now we'll give if time elapsed is greater than 0 also, and the pool dot reserve is pool dot reserve A is not equal to 0 and pool dot reserve B is also not equal to 0, then in this condition will be update all the cumulative prices for the oracle. So price 0 cumulative last, the pool ID, we are updating it, un pool dot into 2, and this complete would be multiplied by the time elapsed. Similarly, we'll be updating the cumulative price of B as well. So here we'll replace B by A, A by B. That's it. This was all about a function update. And now to this, we'll be giving block timestamp last, the pool ID that's equal to block timestamp. So this will say the last timestamp. So this was all about our complete contract. This was the core smart contract of the project, the RSKDex.sol, that have implemented a decentralized exchange using the AMM model, that is automated market maker. So it allows users to create a liquidity pools, add or remove liquidity, and swap ERC20 tokens using a constant product formula. This contract, which we have built, also includes the built-in fee handling, slippage protection, ring transfer protection, price tracking. So it is just a simplified, yet it is a secured Uniswap style DEX on Rootstock. Now we'll go on creating another contract. For that, in SRC, we'll create one more folder and we'll name it as mock. Inside this folder, we'll create a new file as mock ERC. So this is a contract, mock ERC20.source. It's just a simple ERC20 token that will be used for testing and development. So this contract is for easy minting. So let's go on writing this contract. First we'll give our license identifier, SPDX license identifier, then our Solidity compiler version, Dogma Solidity. I'll give it as 0.8.9. I'll go on importing. First we'll be importing ERC20 token, ERC20, ERC20 dot, and this import is a standard ERC token implementation, which has been taken from OpenZeppelin. This will give us ready-made functions like transfer, balance off, approve. Now contract mock ERC20 is ERC20. This is a declaration of a new contract that's named as mock ERC20, and it will inherit all functionality from the ERC20 contract which are imported. Now we'll give the constructor memory name, string memory symbol, ERC20 name and symbol. So this will a construction that will be run. So once at a deployment, we have initialized the ERC20 token with the name and symbol. Now we'll go for minting. So mint message will give this tokens. So we are minting this much amount of tokens to the deployer's address, and this we give it because this is used because ERC20 tokens uses 18 decimal places. So this much amount of tokens will be given to a deployer's address with this much amount of decimals. Then function mint address to UN250. We're just publicly calling a function to allow the minting new tokens, and it's calling it externally from the contract mint to amount. So this mint to amount will create the specified amount of token and we'll just assign them to give it address. So that's it. This was all about the mock ERC20 contract, which is created for mock ERC token 2022 for the testing purposes. And on deployment, we have just given this 1 million tokens are mined to the. That wraps up part 1 of our DEX series. We have written the core smart contracts which allow us to simulate the real token swaps in a controlled environment. This gives us a solid foundation before moving on. So in the next part, we'll write the deployment script and the test file and then deploy the DEX to see it running end to end. Thank you.